Okay, Royals. In lesson 6.6, we started dealing with algebraic vectors. Students that were familiar with geometric vectors from a course like physics might not have as much familiarity here. So make sure you spend some time with it. The concepts don't need to be that difficult, but there is some new stuff here. So first thing that I want to do is take a look at these quick little formulas for magnitude and direction in 2 space, or R2. Meaning we have only 2 dimensions, the x-axis and the y-axis. Right. So we said that any vector, any magnitude and direction, say like a vector of magnitude 5 units that is, or I don't know, some number of units that is east 30 degrees north, could be represented by just one ordered pair, with the understanding that its initial point could be placed at the origin. Let's call this the point P over here at A comma B. Then that right there, by giving just those 2 components, maybe you shouldn't say coordinates, it's the coordinates of the endpoint, but it's also going to be the component of the vector. I'm defining a direction and a magnitude. For the direction, we could say that the tangent of theta is going to be given by the ratio of b over a. Just be careful about what quadrant you're in. Should work okay as getting an angle in standard position. As long as you report it in standard position, your calculator won't always give you the standard position angle. And then for the magnitude, let's call this vector v here. I can say that the vector v is given by these components. And in the lesson, I said some texts will use different brackets to try to differentiate between a point. I don't really think that we need to do that, though. This is obviously not a point because there's an equal sign there and there's a vector symbol to the left. So use the context of the question. The magnitude of that vector is going to be given by the square root, only the positive root of the sum of the squares of the components in R2. And what I want to do is develop that formula with you in R3 a little later. Okay. What else do we want to talk about? The I hat, j hat, and k hat. Let's go to 3 dimensions then. So the right-hand system, I think you might be better doing a Google search for this if we haven't had a chance to talk about it together in person. The idea of the right-hand rule is when you draw your axes in 3 dimensions, you really want to know in what direction is the direction of increase. And this is where I'm kind of picky about arrows on our axes. Here I was taught that the arrow goes on the direction of increase of the axis. So usually what we do is we decide to just keep the x-axis, or make the x-axis be this axis coming in and out of the page. So there's the positive x-axis there. And then if we decide to have the positive y-axis, or the positive direction of the y-axis going to the right-hand rule says I point my pointer finger in the direction of the positive x-axis, I curl my middle finger in the direction of the positive y-axis, and then my thumb will, point in the direction of the positive z-axis. Now you can rotate this around in any direction that you want. You can draw it in any direction that you want, but notice that the right-hand rule will still be satisfied. Okay. The other thing that you need to wrap your head around here is that we are, like what we were doing in grade 11 for 3D trig problems, we're drawing in perspective. So that right there is a right angle. And if that bugs you, just take the corner of your page that you know to be a right angle and put it in perspective. Doesn't that kind of look like 120 degrees? Right there. This isn't a mattress, by the way. This is just the, I don't know, what do you call that thing that goes underneath a tablecloth? Like a mat or something. There you go. So the I hat, j hat, and k hat, I hat, j hat, k hat, those are the unit vectors in the direction of the positive axes. I hat in R3 is 1, 0, 0. J hat in R3 would be 0, 1, 0. K hat in R3 is 0, 0, 1. There is no k hat in R2 because you don't have a z direction in R2. So you want I hat and j hat in R2, it's going to be 1, 0, and 0, 1. You could argue that I hat in R4 is going to be 1, 0, 0, 0. I'm just going to I have a hard time drawing a 3-dimensional diagram on a 2-dimensional surface. I'm going to have a hard time drawing a 4-dimensional diagram on a 2-dimensional surface. Again, look up Google, see what you can find. Okay, sketching in R3. To help us sort of develop the idea of magnitude, and then I'll see how I can do, we'll see how I do with these direction cosines. So imagine you're asked to sketch the vector, well, I don't know. I was going to pick numbers. Let's just keep it algebraic, a comma b comma c. Let's assume that a, b, and c are all positive. Then what I'm going to do is I am going to find the position A on the x-axis. I'll find the position B on the y-axis. I'll find the position C on the z-axis. To me, it looks like I might be drawing something like maybe, I don't know, 4, 3, 2. These rectangles that you can draw, try drawing a rectangle. I think maybe the safest one or the easiest one to do is in the YZ plane. So this YZ axis together makes a surface called a plane. It's a vertical plane. And the reason why most students find this rectangle the easiest to draw is because it will actually look like a right rectangle if you're facing the page like that. The other rectangles are going to be in perspective. Go forward A and then right B. Go right B and then forward A. And you'll show the commutative property of vector addition, that a plus, or a comma 0 comma 0 plus 0 comma b comma 0 is the same as 0 comma b comma 0 plus a comma 0 comma 0. So like the coordinates of this point right here, I suppose, would be a comma b comma 0. Coordinates of this point are a comma 0 comma 0. That point right there is 0 comma b comma 0, 0 comma 0 comma c. Try going forward A and up C. Try going up C and forward A. And those two should meet at the triplet, not an ordered pair anymore, but an ordered triplet, 0 comma A comma C, or sorry, A comma 0 comma C. If you go forward A, right B, up C, or you go up C, forward A, right B, or you go up C, right B, forward A, or you go right B, up C, forward A. There's a number of different combinations. I guess there's what, maybe 8 pathways to, no, 3 times 2, 6 different pathways. Then you'll start to see it looks like we've drawn a prism here. And I think the prism will be useful to sort of visualize the 3D nature of this vector. Because if I just put a point where it looks like that point is right there, like, can you see how this might be interpreted as being, couldn't that point be on the YZ plane, or couldn't it be on the XZ plane, or couldn't it be maybe like in the background on that XY plane? It's very difficult to see where this is and see where that vector is. Or if you try drawing it in 3D, maybe you could even give it some volume to try to get it to look like it's actually coming out of the page at you. You might get the idea that you're drawing a body diagonal of this parallelepiped, or of this rectangular prism. Okay. Now magnitudes. Notice here. Let's call this vector right here the magnitude of vector a comma b comma 0. Now there's just a Pythagorean relationship there, isn't there? That's length b. That length right there is a, so that's going to be the square root of a squared plus b squared. Okay. Now take a side view at that, at this triangle right here. And you've got a projection of a vector onto an xy plane, like its shadow right there, that has a magnitude of the square root of a squared plus b squared. And then you've got a height of c. And we'll call this mag v. And the magnitude of v should be the square root of the sum of the squares of its components. So it's going to be the square of the square root of the sums of the squares of A plus B. I don't know if I could have made that more complicated. Plus the square of C. What is the square of the square root of A? The sum of the square of A and the square of B. That's the sum of the square of A and B plus C. I remember students sometimes being surprised over the next couple of lessons. Some of the things that we're going to learn are actually quite simple, and often the confusion that the students have is maybe a feeling that it shouldn't actually be this easy. But these length formulas actually will generalize into any number of dimensions quite easily. Now, reporting the direction of a vector in 3 dimensions is complicated. If you've ever seen, I don't know, science fiction movie where people are navigating either under the sea or in space, it's kind of hard to just give a number to describe in what direction a person needs to look. You usually give some sort of bearing and then an angle of elevation. One option that we have is our direction cosines. Those direction cosines, my diagram is going to make a mess of it, or I'm going to make a mess of my diagram, are related to these angles here, the angles to the closest, or sorry, the angle to the closest axis there, or the positive x-axis, y-axis, and z-axis. The problem is that these angles are not generally horizontal or vertical angles. They're in skew planes. So imagine, I don't know, this is the vector here, my red pen, and here's the positive x-axis. Then that angle that we really want to standardize as being alpha is the shortest rotation down to there. So I'm going like down and forward to get there. That's alpha. It's not that horizontal angle. It's not this vertical angle that I'm going, and it's not the sum of those angles. The relationship between that angle of elevation and this angle of rotation and that angle of direction is complicated. Again, I'm going to give you a bit of a sneak peek at a projection here, though. What I'm going to imagine is that I'm looking, in what direction am I going to look? I'm going to look at this diagram from here, okay? And what I'm going to do is I'm going to put my eye in the frame so that I can see the positive x-axis, positive direction of the x-axis, and the vector v right there. And the vector v, its endpoint is a comma b comma c. And its shadow, its projection on the x-axis, will be a vector, a comma 0 comma 0. That's just the number of i-hats that you've added. Sorry, it's the number of i-hats that you add right there. Okay, and this angle right here, I know it looks like a vertical angle now, but that's because I've taken that plane and snipped it out and rotated it and flattened it onto my page there. That's the angle alpha. And that's how you can build the ratio that, if we change this to a scalar diagram, this is of magnitude A, and this right here is of magnitude mag V. So I can get a cosine ratio. I can get that the cosine of alpha is going to be given by the ratio of A divided by the magnitude of V. Okay? I wouldn't worry too much about multiplying that to get the scalar, converting it to a unit vector to see that the unit vector will actually have coordinates, cosine of alpha, cosine of beta, cosine of gamma. But it is a way of showing you the relationship between alpha and beta and gamma. You actually don't need to report all 3 angles to figure out the direction of a geometric vector, algebraic vector, sorry. Or geometric vector in 3 dimensions. You only need 2. The third angle will be known if you know the first 2. Look up the formula when you need it in the homework, but we really aren't going to be dealing with vectors in 3 dimensions as algebraic vectors. It's just not practical. And I'll convince you tomorrow, or in our next lesson, sorry, that working with algebraic vectors in R2 and R3 is actually easier than working with geometric vectors. Okay.